Okay, we are recording. Welcome, everyone. This Math219, Clark Bray. Do we have enough seats, by the way? Oh, that's going to be close. There's two more in the back. There's one over there. Hopefully we'll make it. Okay, so I imagine that most of you, hopefully all, certainly most of you got an email from me last week with the sort of initial announcements and the link to the organizational video. I hope everyone's had a chance to watch that video. I know it's tedious, right? I'm sorry to have killed an hour of your time, unless you watch on like double speed, right? Then I only took a half hour of your time. But all of that stuff is really important. It's stuff that has to get said. I feel like it has to get said. It is basically all on the website, but still, I mean, it's all just very important. I'm not going to repeat most of that because y'all watched the video, right? But I am going to repeat the most important two things from those videos. And that is, hopefully no surprise, y'all heard me go on at length about this point. This course is about ideas and reasoning. That's what we do here, right? That's what we're here for. That's really what math is, honestly. This may be in contrast to other math classes that you've had in the past. If so, there's going to be a transition, right? And this is a transition you have to take seriously, and you have to, get on board with how this course is going to go. If nothing else, because on exams, this is what we'll be looking for, is ideas and reasoning. Not just in your responses to the question, but in how the questions themselves are written. Right, what I'm going to be expecting of your ability to actually execute. Okay, so that's again. I went on at length in the recording. I'll keep it short for today. And then the second one is this one here. What is the strategy? How are we going to make learning happen in this class? And again, a lot of classes, the learning happens in class. And then outside of class, there's, a couple of rote, you got a muscle memory, that kind of thing. And again, not really how this class is designed. I don't think that would really be possible in a class like this because there's too much material and it's too challenging. This is a hard class. I don't think that's news to anybody, right? Y'all have probably heard all the rumors. So there's just too much. And so, anyway, heads up. I mean, if you were to take that approach to this class, if you were to think, all right, well, I'm going to do my learning in class, and when class is over, I'll crank out the homework and I'm done. Right? I think that's a really bad strategy. I don't think that's going to work, really. Right? There's just too much. So, again, I won't go on at length, but remember what I think is the goal of class should not be so that you learn as much as possible while you are in class. The goal of class should be so that you can learn as much as possible total, right? Including with lots and lots of self-study time where you're going to learn a lot. I did a lot of this in college, right? I think this is how college classes generally are, well, not always, and there's counterexamples, but this kind of how college classes are largely set up. Okay, so anyway, with all of that said again, let's see here. I'll remind y'all of the class website, not to be conflated with the course website, which is linked here. And again, make sure you've read all of both of the websites. I know it's a lot, right? But again, very important. So make sure you do that. And why don't I pause real quick? Whoops. Let me pause real quick for questions. Anybody before we dive in and do some math? Everybody on board with the plan? Okay. All right, good deal. Let's do it. Okay, so a little bit of an introduction at first. Why is multivariable calculus important? Why are we here? Why are you taking this class? Of course, the obvious answer, because you are required to in most cases, right? So the natural rephrase of the question, why does your major require that you take multivariable calculus? And so I think this is a very reasonable question and worth addressing before we dive in and focus on a bunch of multivariable calculus. I hope you're already bought in on the idea that single variable calculus is important. Right? I mean, y'all are presumably reasonably proficient with single variable calculus, and you've not only know how to compute derivatives, not only do you know how to compute integrals, but you know how to apply derivatives, and you know how to apply integrals, right? And so in particular, derivatives and integrals, well, derivatives help you understand how things change. Well, that's a pretty broad category of applications. Stuff's changing all the time, right? So pretty obvious that that's going to be important. And the way I like to phrase what integrals are good for, a lot of people misunderstand and think integrals are about computing the area under a curve. Not really. That's a piece of geometric intuition, I suppose. It has its moments. Rare circumstances, your end goal might actually be to compute an area under some curve. Like if you're painting the side of some weird building that has a strange shape or something, you know how much paint to buy? It's very rare. It's not usually the point, right? The reason that we care about integrals, the reason that people who are interested in applications care about integrals, it's not because of area. It's because the things that you can compute, right? Any, what I like to call accumulating quantity. Any quantity where the whole is the sum of the parts. Right? Integrals are a tool for then breaking it up into corresponding parts and doing that, sum of those parts to compute the whole. Right? Well, there are a lot of quantities where the whole is the sum of the parts. Right? That's what integrals are good for. So again, really broad category. Okay, that's all single variable. Let's talk about multivariable. Right? We live in a three-dimensional world, for example. Right? Now, a couple of low-hanging fruit, sort of obvious applications. Here's a reasonable one. Let's suppose, here we are in a room, right? And we can talk about the temperature in this room. By the way, we can literally talk about the temperature in this room. Is it too cold, too hot? Y'all doing okay? All right. Okay. Sorry? All good? Okay. All right. Yeah. So, we do have a thermostat over there, so if anyone gets cold or hot, we can talk about which way to go with it. So in general, though, temperature depends on position. The temperature over there by the door, sort of at floor level behind the trash can, it's a different temperature than over by the window, or let's say that window that's got some sun coming in. It's probably warmer over there, probably colder over there. Right? So temperature is a function of position. We have here then that temperature is a function with three input variables. You give me X, Y, Z, only then can I tell you what the temperature is, because I need to know where you're talking about. Well, if you have a function of several variables, and then let's suppose that I'm at this point right here, and let's suppose that I am moving with some velocity, that means not only is my location changed, not only am I moving a certain number of feet per second, right, but I'm moving at some weird angle. How do I account for the angle? If I want to compute the derivative of temperature, right, how fast is temperature changing? How do I account for the fact that I'm moving at some angle? Well, that's a non-trivial question. That's something we're going to have to figure out. This is a easy first example of why we're going to be interested in multivariable derivatives. And short answer, summary is because we live in a three-dimensional world. This is very real world. This is how if you want to know stuff like temperature, well, temperature is a multivariable function. So we're going to answer this question in this class. Here's another question. Let's suppose you have a lump. Maybe it's a rock. Whatever. Who cares? Some lump of stuff. And suppose you know the density, but wait, slow down. Density is not going to be a constant. Again, real world. How is the actual real world put together? Very often, the density depends on position. Just like temperature in this room depends on where you are. It's different at different locations. Likewise, in the real world, very often, density is not a constant. So, how are you going to compute the total mass in this region? You can't just multiply the volume times the density because the density isn't constant. And it's tempting to say, I'm sure you all remember from your Calc 2 classes, Calc 1 or 2, probably Calc 2, that, we could take slices, right? And maybe on the slices, the problem will be easier. Well, what if on the slices, the density is still not constant? Right? So if you look back into your Calc 1 or Calc 2, your single variable calculus notes on problems like that, you will notice that they very carefully set it up so that on your slices, the density is constant. Again, it's not very real world. So how are we going to deal with that? Density is not constant in any direction. How do I slice it to be able to compute? Again, the whole is the sum of the parts, and this too is something we're going to answer in this class. Everybody seeing how this is real practical, rubber meets the road, real world kind of stuff. Yeah. Okay. All right. So here's an econ example. In fact, I'm going to show you some applications in different fields of study. What I like about these examples is they're so intuitive and relatable, but they are also seemingly kind of trivial. Who cares how much the rock weighs? Put it on a scale, right? It doesn't seem that important. I'm going to show you some non-trivial, like sophisticated, arguably scary examples. Right, and point out how multivariable calculus is going to help with those too. So here's what I'm going to call I'm going to call it an economic model. It's not. I made this equation up. But the point is, this is kind of what a lot of economic models look like. It's usually not, price equals formula. It's usually, I don't really know the formula for price, but I know that this combination of labor and price minus this combination of price and capital and blah, 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 I know that these quantities have to relate in this way. And you may or may not have solved for the variable you're interested in, and you may or may not be able to. Notice in this equation, you can't solve for P analytically. You just can't do it, right? It's transcendental in P. Forget about it. Okay, well, all right, but I want to know how much price is going to be changed. How fast is price going to change? In particular, let's suppose I have control over these things, or either control or I have the ability to measure or anticipate how fast are these things going to change. And based on my knowledge of how these things change, how can I use this equation that relates these variables to P? How can I use that to infer how fast P is going to change? This is a very natural question, and it's also pretty non-trivial. Scary even looking. So this is something that we're going to talk about in this class. Right? So if you're an econ major, this is one of many examples of reasons why you're going to need to know multivariable calculus, reasons why the econ department requires taking a multivariable calculus course. And of course you have options, but I think this is a good one. Okay, by the way, just a real quick observation. Notice we have 5 plus 1 variables. Right, we got 5 quantities that are all dependent on time. That's arguably a total of 6 variables. I'm going to make the modest observation here that apparently studying multivariable calculus with only 3 variables is pretty easily seen to be insufficient. Right? I didn't do any weird, sci-fi, 4th dimension, time travel nonsense to come up with an example where we need more than 3 dimensions. Right? I've always thought this was weird that a lot of books will restrict their attention to 3 dimensions. And the idea, I suppose, is that we only experience 3 spatial dimensions. Sure, absolutely. I have no intentions of preparing y'all for going to the fourth dimension, right? But we don't have to. The point is, spatial dimensions are just not the story. This is economics. There's nothing sci-fi about this at all. And we need to be able to do math in 6 dimensions, apparently. At least 5, depending on how you choose to look at it. Is that cool? Everybody happy? Now, I say that not to freak you out. Don't worry, I'm not going to ask you to draw any 6-dimensional pictures, because you can't, and neither can I, and neither can anyone, right? But we do need to be able to actually do some math, and it turns out that there's a lot of multivariable that you can do in 6 dimensions based on intuition that you will develop in 3 dimensions. And that's going to be plenty good enough for our purposes. Okay. There's some scary looking stuff. Right? In fact, let me get to full screen mode. There we go. Okay. Wow. Isn't that scary looking? I remember the first time I saw these equations and I was super intimidated. Right? Well, after this class is over, my goal is that you should look at this and be like, yeah, sure, of course. Well, maybe not obvious, but ultimately this is not really saying anything too shocking eventually. So various things we're going to have to do. We're going to have to figure out what this means. We're going to have to figure out what this means. That's a weird one. Is that a differential, but it's a vector? Strange, right? So we're going to have to figure out what these details are. We're going to have to figure out what this construction means. Wait a minute, that's an integral that involves a dot product? That's strange, right? So what's going on? What does this mean, and what does it represent? So that's one thing we're going to have to do. We're also going to have to understand, what is the intuition behind it? I mean, it's one thing to be able to write this down and be able to compute it. What does it represent? What does it look like? How should I think about that? Right? We're going to be doing that in this class. Then we're going to be talking about why should these two things naturally be related to each other? There is a point of view that says, well, yeah, of course. So, what is that, right? How is it that I should expect that these two seemingly different, weird, scary-looking expressions should be equal? Right? That's going to be another one of our goals, to understand this equation on sort of that level of intuition. And it's going to be very late in the course. We got a lot to do to build up to that, so don't try to do it now, right? But we will eventually make good sense out of that. And then lastly, once we understand the notations and the constructions and the equations and the intuition behind those equations, what does that help me understand about electric fields? How can I understand electric fields better as a result of all of this math stuff? Right? And I feel like we're going to find some good answers to that as well. Okay. So I think it's a fairly uncontroversial take that understanding multivariable calculus is, 80% of the effort of understanding Maxwell's equations. It's mostly just understanding multivariable calculus. Right? So if you're an engineer, if you're a physicist, if you're a chemist, right? Well, that's a pretty good reason right there that you need to know. Is y'all buying what I'm selling here? It seems pretty believable? Okay. All right. Okay, last example I'm going to give, and there's really not much we can do with this. This is not an equation that we're going to study in this course. This is a partial differential equation, but it's a very important partial differential equation called Schrodinger's equation, and it's of fundamental importance in quantum mechanics. And quantum mechanics, of course, you're going to do a lot of that if you're a physics major. If you're an engineer, you're going to need to at least kind of know a few things about quantum mechanics. And chemists have to understand molecular bonds. Molecular bonds are determined by how electrons behave, and how electrons behave is dictated by Schrodinger's equation. Okay. So lots of uses for this, and this object right here is an object of multivariable calculus that we're going to study in this class. Not the whole equation, not how to solve the equation, but that object is something we will discuss. Okay, so that's the pitch. The sort of pithy summary is multivariable calculus is the calculus of the real world. It's the world that we live in. How do we actually get stuff done? Single variable calculus, maybe a little bit sometimes. Most of the time, multivariable calculus. All right, let me pause. I have a tendency, if you haven't noticed already, I have a tendency to kind of get on a roll and do all the talking. Does anybody have any questions that you've been hoping to try to fit in without opportunity? Okay. All right. Okay, so here's something y'all are going to see a lot of in my lecture notes, this comment right here. As I was preparing to teach this class, there's, again, so much to say, right? So much I want to be able to help y'all with, so many ideas to communicate. And as I think I've written somewhere in the website, and I think I said a few words about this during the recording, I have to make tough choices as to what do I spend class time talking about. We can't do it all. It's not possible. Too much. Can't happen, right? So I have to make these tough choices. On the other hand, the things that that don't make the cut, that I don't have time to talk about in class, I still want to be able to help, right? And so now, of course, I can't write 1,000 pages of lecture notes. You probably don't want me to do that either. But there are some things that I have written into my notes to be helpful, but that we won't actually spend class time on. Heads up for these gray shaded boxes and this note at the top. When you see something like this, that's your cue that you probably ought to go back and read this after class is over. Because it's important enough that I did feel it necessary to write it down, right? But it's probably also in the book, in most cases, not always. Okay. All right. So that said, I will usually skip most of that stuff in class. I do usually I will say a couple of quick words, and here's what I'm going to say about this. This point P1, and keep in mind there is a kind of a pairing between points and vectors. Points and vectors are not the same thing, but if you have a point, you can interpret it as a vector. If you have a vector, you can interpret it as a point in the usual way, right? In particular, a point you think of as a vector by way of the arrow whose tail is at the origin and whose head is at said point. Right? Does everybody remember that from probably first day of class in Math219? Okay. All right, so if that's P1, thought of not as a point but as a vector, and if this is P2, thought of not as a point but as a vector, notice that this thing here that a lot of people like to write that as P1, P2, because, well, look, it starts at P1 and it ends at P2. So this notation kind of makes sense, I suppose, right? I think it makes loads more sense to write it as P2 minus P1. Not hard to persuade yourself. If you add as indicated, then that checks out, right? So that works algebraically. So why would I prefer this notation over this notation? And the short answer is algebra is a good thing. Algebra is your friend. Don't hide it. Right? There is a subtraction hidden inside of this notation. Why would you hide something that could be useful? I don't think that makes any sense at all. So I, all day, every day, will write this as P2 minus P1. I almost never write this. Again, just trying to make a pitch. You can write it that way, and a lot of books will use that notation. Anyway, okay. How we doing? All right, last little quickie thing. This is just another notational thing, but very often we'll need to represent vectors x comma y comma z. Very often it's convenient to think of those as not as points but as vectors. And again, there's kind of a duality. You can think of a point as a vector and vice versa. A very, very common notation is to call this R. Pros and cons, but anyway, that's the very common standard. And okay, fine, call it a standard. So heads up for that. When you see R vector, that almost, well, it should by default probably be assumed to mean x comma y comma z. Note, in the past, I have chosen to write this as x, cueing off the fact that the first coordinate is x. And, I find that it avoids certain problems. Calling this R does have certain downsides that this avoids. But anyway, the pros and cons are not the point. The point is that when you look at my old tests, very often you will see this notation. For this semester, I will be using this notation. So when you see this on my old tests, you should think that. Okay, moving along. So this next topic you probably haven't seen much of, parameterizations. It's a really important idea. This is something we're going to do tons with. Very valuable. Very valuable as a computational tool, if nothing else. So really important to know. A parameterization is a function. Specifically, it gives position as a function of a single parameter. This is for a parameterized curve, and I'm going to think of that parameter typically as being time. So position is a function of time. Y'all have probably thought of this before. Maybe you might not have seen the term parameterization, but the idea that position is a function of time, that goes all the way back to Calc 1, right? You've got a car driving along a road, and you know information about the speed of the car, and you want to compute the position, where is it, at what time, that kind of thing, right? Position is a function of time. So that's all a parameterization is. See some examples. This is, I think, a really good starter example. Notice first, this parameterization, this is a function. T is the input. X and Y are the outputs. That makes it a function. Inputs and outputs. Again, notice that time is the input and position, X comma Y, otherwise known as the R vector, right, is the output. Okay, now this particular parameterization, is like so. X is cosine of t and y is sine of t. So this is a parameterization of something. It does give me x and y, and therefore position as a function of time. But what is this thing? It's a little scary to look at initial glance because you think, oh, sine waves and cosine waves. And is this a scary looking weird thing? Not hard to persuade yourself, though, that keeping in mind that this is just x and that this is just y, notice that these points, x comma y, satisfy that equation. That means that every point that comes out of this parameterization, every position, no matter what time you're interested in, every position is on the unit circle. So, in fact, this is a parameterization of the unit circle. Everybody see that? All right. Here's another example. Let's see here. Let me just do like so. So there's a parameterization. I got two outputs, x and y, are functions of position. Side note, notice I did not explicitly indicate that this one's called x. Kind of implied by the fact that it's the first one listed, right? And likewise, I didn't explicitly call this y, but part of your job as in, properly interpreting these things is to remember that's the second output. We should probably call that y. So what is this? The method that we just used up there was, roughly speaking, I looked at sine and cosine, and that just kind of made me remember the Pythagorean relation, right? So do these formulas remind me of anything? Nope. Okay, so I'm going to have to try something different. Here's how I'm going to encourage y'all to think about this one. Again, not forgetting, that's x, and that's y. What you can do in a situation like this one is first solve for t in one of those equations, and then second, plug that in to the other equation. Y'all see what I did there? We solve for t in the first equation and then plug that into the second equation. Because after all, this, let's see here, this right here is just, that is the formula for y, that is that second equation. And notice, everything worked out fine and dandy, and the punchline is I have a, oh golly, let's see here what color I have. Okay, here we go. I have the equation of a line, right? So this thing here, get rid of all of the mess, this is just a parameterization of that line. Everybody see how that worked? Okay. All right. Okay, now here's another way you could do it. I look for, so again, I have this formula for x. There it is. And I have this formula for y. Here it is. And I notice that there's kind of a relationship between these two formulas. T minus 1 and 3t plus 4, they're not the same, but they're both kind of first degree polynomials in t. Right? They got a lot in common. And when you notice something like that, sometimes that means it's pretty easy to turn one into the other. Said differently, it's pretty easy to manipulate the equation for x to produce y. And when you do that, notice the result is an equation. And in fact, in this case, how about that? Same equation. So a different way to get to the same result. Just kind of notice, when you see a relationship, the manipulations that you do to turn t minus 1 into 3t plus 4 are the manipulations that turn x into y. Because that's what they are. How we doing? All right, so I want to pause real quick and point out I have given y'all now 3 different ways to recognize parametric curves from the parameterization. There's the notice that you got lucky method. There's the solve for t in one of the equations and plug that into the other equation method. And then there's the notice the relationship method. 3 different methods. Why would I give you 3 methods for doing the same thing? And the answer is that none of these methods can be relied upon always to work without exception. Right? This is what I like to call, one of my favorite metaphors. You're going to hear me saying the following a lot, is you have to develop a mental toolbox full of various tools. And sometimes you need a hammer, sometimes you need a screwdriver, sometimes you need a torque wrench. Different circumstances, right? If you only have a hammer, it's not really good for when you need a screwdriver, right? So it's I think it's good to develop various tools to become comfortable with various tools. Let's think about how these might go wrong. Pretty easy to see how this might go wrong. Maybe I just don't get lucky and happen to notice a convenient relationship between the formulas, such as I get lucky here. What's wrong with this one? I might not be able to solve for t. What if the formula for x is a 5th degree polynomial in t? I can't solve for it. What might go wrong with the third method? I might not see any obvious sort of algebraic relationship between those expressions. So these are just sometimes solutions, and the more tools you have, the more likely you'll be able to solve any given question you encounter. Does that make sense to everybody? So don't think of this as, here's how you do them, right? The algorithmic sort of, plug and chug. Now you do have to rehearse each one. Well, certainly these last two. You have to practice them to the point where when they do apply, you are proficient with turning the crank and getting an answer. Absolutely, right? But it's also important to be able to look at these methods and think to yourself, okay, what's it going to cost me? How, under what circumstances do these work? Under what circumstances are they hopeless? Right? You want to familiarize yourself with the methods and then get good at associating the right method to whatever given problem you're looking at. Okay. All right. Again, if you have any questions, just go ahead and shoot that hand up. It's no problem. Okay. All right. Here's a three-dimensional parameterization. Notice 3 output variables. So this is X, this is Y, and this is Z. Okay, how are we going to identify what that is? By the way, you can't just aim to produce an equation. An equation of 3 variables produces a surface. We'll talk more about that later. We know this is a curve because position is a function of time, always traces out a curve. So an equation is kind of out of the question. So how are we going to help ourselves to understand this thing? Well, it's another tool for your toolbox. I'm not saying the following will always work. I'm saying this works sometimes, and it certainly works here. Let's start by thinking about just X and Y coordinates. Right, this is what we call the projection to the XY plane. We're going to ignore Z. Right? Wherever you might happen to be in space, if you just ignore Z, then effectively you're looking at the projection, sort of the shadow down in the XY plane. Is that cool? Okay. Well, looking only at X and Y, I recognize that. Lucky break. Boom. We already know that's a circle. By the way, this is not rare. This little combination of expressions, right, comes up a lot. Hopefully no surprise, the world is full of circles, right? So it very naturally arises pretty often to see a cosine t and a sine t. And so the punchline then is that the shadow in the xy plane is kind of going around like so, what you might call counterclockwise. I'll say counterclockwise as seen from above, right? Perspective dependent. That's what the shadow of this curve looks like. It's not the whole curve, but that's what the shadow of the curve looks like. And then I can say, all right, what's going on in the sort of Z? Forget about X and Y, let's just think about Z only. And well, again, that's pretty easy to do, right? Looking only at Z, how does Z vary with time? Z is time, right? As t increases, Z increases. So what we've got then is we've got a curve, whatever this curve is. Altogether, this is a curve whose shadow is doing this and whose z-coordinate is rising like that. And you use your geometric intuition. By the way, there's going to be a lot of that in this course as well. This course is unavoidably, I'm going to say, kind of intrinsically geometric, right? So don't try to avoid the geometric intuition. You got to use your geometric intuition. If a curve has a shadow doing this and the altitude is kind of going up linearly, that's going to produce a helix, kind of a spring sort of a shape. Yeah. Okay. Let's take it the other way. All the examples I showed you so far, I gave you the parameterization, and the question is, what else can I understand? How else can I understand that curve? Now let's turn it around. What if you already know what the curve is in some other sense, and you want to produce the parameterization? I think the book is a little short, frankly, on good examples, and focus on the importance of this because, well, anyway, the reason I think it's important is that this is what I experienced when I was y'all's age, and for the 10 or 15 years after that, lots of circumstances where I knew something about the curve and I needed to produce a parameterization. The real world very often does not just hand you the parameterization that you need to work with. Right? So how do you produce a parameterization? And here's my favorite method. I call it anyway, the graph parameterization method. Something we'll spend some time talking about later is what is this word graph? Very commonly, I'm going to say misused. A graph is the word graph is not synonymous with picture. A graph is a very specific kind of picture. It's a very specific construction to understand a function, and that is you set the value of the function equal to a new variable. So if you want to understand some function of x, if you set that equal to y and then draw the resulting curve, right? This is called the graph of that function. We'll talk more about graphs later. But because this is a graph, I'm going to use what's called the graph parameterization, and here's the big idea of the graph parameterization. It's super simple. Let t be the input variable. That's all it is. Super simple. It's one of the easiest methods in the entire course. Just let t be the input variable, and everything will just fall into place. So in particular, let's look at this curve right here. First, notice that it is a graph. It's a graph of this function. F of x is x squared. Okay, now I'm going to do exactly what the method says. The method says let t be the input variable. Okay, the input variable is x. Let t be x. Cool, done. There it is right there. Just let t be the input variable. And I claim that I'm basically done at this point. It's all just a matter of following my nose at this point. If I've let x be t, then I kind of don't really have any way around that y has to be t squared. Everybody see what happened there? So, again, so easy, right? All I gotta do, just let t be the input variable and then sit back and watch your parameterization just take shape. Super easy to follow, works really well. Here's another example. By the way, I like this example because it doesn't, at first glance, look like a graph. But it is, right? So you gotta watch out for these sneaky graphs, right? Heads up for that. If you have a sneaky graph, well, write it as a graph. Now that it is a graph, notice, let's see, this is a graph of this function right here. What is the input variable for this? Well, y now is my input variable, and following the usual instruction, letting the input variable be t. And notice, kind of don't have any way around that x then has to be that. And again, boom, parameterization made. Cool. Okay. Here's a tweak, a twist. Here, I don't have. Oh, sorry. Go ahead. Yeah.
Did you turn y to t instead of x to t in the previous example just because it was easier to solve for x?
It is, yes, it's easier to solve for x. And in fact, I would say it is only possible to solve for x. Yeah, I mean, in a sort of, pen and paper algebraic sense. Yep.
So
totally.
t being the input variable could be for either.
Yeah, totally. Yeah, however it is that you choose to write your equation as a graph, and sometimes you have options. Yes, sometimes you could do it either way. Knock yourself out. It doesn't matter. It's all good, right? Whichever way you have written it as a graph, let t be the input variable. Yep. Okay, so yeah, tweak. Here I don't have any rectangular information about this curve. I have polar information. And by the way, we are going to talk about polar coordinates later in this class. Just for real quick purposes, this is the idea. Right, the idea is that theta represents this angle and r represents this distance. You'll see why I do air quotes. I'll talk more later about why I put the air quotes on distance. But based on this picture, hopefully not hard to see that we have these standard relationships between x and y and r and theta. So, okay, fine. Well, this isn't rectangular. How am I going to use the graph parameterization? And it's still just a matter of plugging in. You just have to write down these conversion formulas, which, by the way, very soon you will have memorized. And then, yeah, just kind of plug in. I mean, if this being as it is a polar graph, right, I've got one of the polar variables solved for, as it were. A function of one of the polar variables I'm setting equal to the other polar variable. Well, the input variable is theta, but whatever. Just take this formula for r, plug it in here, and check it out. I now have, as desired, position as a function of a single variable. Now this time my single variable is theta. Whatever. You can rename it and call it t if you like. Doesn't matter. It's fine. But position is a function of a single variable. Yes?
What does the NB stand for?
What is the what?
NB.
Oh, yeah. This is a standard abbreviation. I think the original is Latin. I want to say it means like nota bene or something like that. Anyway, it's just a heads up. Hey, it's just a pay attention to this. That's all it is. Yeah. By the way, good question. Very often in this class, I will write things down or say things that I was just assuming that everybody knows, possibly inappropriately, right? So if you don't know what something like this means, please ask, right? I'll be very happy to clarify. Okay, last little detail about this example. This construction is called, I like to call it anyway, the polar graph parameterization, in recognition that we started with a polar equation. But it remains, very importantly, for any parameterization, when we say position as a function of time, parameterization means position in rectangular coordinates. Very important. It's got to be position in rectangular coordinates. Okay. All right. Okay, let's see here. We have 2 minutes. Okay, let me get the ball rolling. Oh, no. What an unfortunate pun. Let's get this started. Just a little bit and get this started. Suppose I have a bicycle wheel, and that bicycle wheel is rolling along the ground. The x-axis is the ground, and it's rolling to the right. Y'all have probably seen this in the real world at some point, that a bicycle, dusk or something like that, the street lights are on, and the bike is going down the street, and that reflector is making a weird kind of choppy shape. So let's parameterize that curve. Basically using vector algebra is going to be the insight here. There's also a lot of little details, and we'll talk about the details next time. But the big picture on this is to recognize that the axle is actually pretty easy to understand. The axle of the wheel, it just goes along in a straight line. Nothing to it. Right? And then the other part of it that gets me to where I need to be is what I'm going to call this D vector right here. That's the displacement from the axle to the reflector, wherever the reflector might happen to be at any given moment. So, let's say the reflector that started there after the wheel has rolled, the reflector goes up to there. Fine. Well, from the axle to the reflector, this little purple vector. And here's the thing. That purple vector is relatively easy to understand. That purple vector is just going around a circle. And that's going to be sines and cosines, and there's details. We'll talk about the details next time. But basically, this wacky curve that the reflector is following, at a glance, looks like it would be super hard to parameterize, but it's the sum of two much simpler things. The axle is easy, and that D vector is easy, and vector algebra tells me that the reflector is just the sum of axle plus D. So anyway, I'll say a few words about the detailed doubles next time, but that's going to be the big picture. Nice to meet y'all. Hope you have a good rest of your day. See you on Wednesday. Yeah, sure, my pleasure.